Let's say you were given the following trigonometric equations and you were required to solve for x. In this lesson, we will learn how to solve these equations for specific values of x and also learn how to determine the general solutions to these equations. Let us now look at example 1. Here you are required to solve for x where x is in some particular interval. The very first problem, or problem A, says sine x equals to plus 0.35. Now, to solve a trigonometric equation, you must make sure that you only have one trigonometric ratio on the left and some numeric value on the right. So in any case where you find a complicated equation, you have to simplify first so that you are left with one trigonometric ratio on the left and some numerical value on the right. For our problem A, this is already in a simple form. So all we have to do is to follow this approach in order to solve for x here. The first thing that we do is to calculate the reference angle. Remember how you calculate the reference angle? You simply punch your second function or shift and then sine, then 0.35. So it will be shift or second function sine of 0.35. That will give you an angle of 20.5. So let's have a look at this. So if you say shift sine 0.35, you'll get an angle of 20.5 if you round to one decimal place. Now, this is how we find the reference angle. Now, you look at the function that you've been, or the equation that you've been given. Sine x equals to positive 0.35. This tells us that we are interested in the values of x where sine x is positive, because the value that we've been given here is positive. Sine x is positive in the first quadrant and the second quadrant. Now, since sine is positive in the first quadrant and the second quadrant, that means our reference angle will also form part of the solution. So the 20.5 degrees will be our first solution of x in the first quadrant. Now we have to find another solution in the second quadrant. In the second quadrant, we have 180 degrees minus theta. So another solution of this will be 180 degrees minus the reference angle, which gives us 159.5 degrees. Then we write the final answer. The final answer, we know that x is 20.5 degrees or 159.5 degrees. Let's now move to problem B. We said in order to solve a trigonometric equation, you must only have one trigonometric ratio on the left. It must not have coefficients, just the trigonometric ratio. So we have to simplify this, and we take 4 to the other side. Then we have cos x on the left equals to half. Then we find the reference angle. Shift cos 1 over 2. That will give us 60 degrees. This equation tells us we are interested in the values of x in the quadrants where cos x is positive. Cos x is positive in the first quadrant and the fourth quadrant. So it is positive in quadrant 1 and quadrant 4. Since cos is positive in the first quadrant, that means our reference angle will also form part of the solution. Now we can go and find the solution in the fourth quadrant in 360 degrees minus theta. So which is 360 degrees minus the reference angle, which is 300. Then we can write the final solution as x equals to 60 degrees or 300 degrees. You must take note that it is not always the case that the reference angle forms part of the solution. Let us move to problem C. Problem C, you have 1 over 2 tan x equals to minus 1.4. We said on the left hand side, we must be left with only one trig ratio. Then we can multiply the right hand side by 2 so that we only have minus 2.8 on the right, and we have a trig, only one trigonometric ratio on the left. Then we can find the reference angle, shift or second function tan 2.8. You must have noted something. When you find the reference angle, you don't use the negative sign. Look here, we have tan x equals to minus 2x. So to find the reference angle, we try to find the positive acute angle. So you are going to, or the positive angle, which will be our reference angle. In this case, instead of writing minus 2.8, we write only the positive. So you only take the positive value. Now, the arctan of 2.8 is 70.3 degrees. Therefore, this is our reference angle. But this sign here tells us that we are interested in the values of x in the quadrants where tan x is negative. Tan x is negative in the second quadrant and the fourth quadrant. So in quadrant 2 and quadrant 4. That means 70.3 degrees is not part of the solution because this is in the first quadrant. Now let us find our first solution. Our first solution is in the second quadrant, 180 minus the reference angle. This is in the second quadrant. That is 109.7 degrees. Another solution is in the fourth quadrant in 360 degrees minus the reference angle. That gives us 289.7 degrees. Then we can write the final answer as the answer is x equals to 109.7 degrees or 289.7 degrees. 70.3 or x equals to 70.3 degrees is not the solution because we are only interested in the values of x where tan x is negative. Let's try problem D. This one is already simplified. On the left hand side we only have sine x. On the right hand side we have minus 0.5. That means we are interested in the values of x in the quadrants where sine x is negative. Let's find the reference angle. Now, we said we only take the positive value. We've been given minus 0.5, but we only take the positive value when we find the reference angle. The arcsine of 0.5 is 30 degrees. Now, we are interested in the values of x in the quadrants where sine is negative. Sine is negative in the third and the fourth quadrant. In the third quadrant, we have 180 degrees plus. So this is the third quadrant. So we're going to say 180 degrees plus the reference angle, which will be 210 degrees. And it is also negative in the fourth quadrant in 360 degrees minus. So it will be 360 degrees minus the reference angle in the fourth quadrant, which gives us 330. Then we can write the final answer and say the final answer, x is 210 degrees or x is 330 degrees. Let's now look at the general solutions. General solutions, in this case, we just find the solution that works for all the values of theta without any interval. We are not given a restriction as to which values of x we should find. We've been given sine theta equals to 0.3, and we have to solve to correct to one decimal place. We know the steps. We have to first find the reference angle. In this case, on the left hand side, we only have the sine of theta and some numeric value on the right, so we can simply move on to find the reference angle theta. We second function or shift, depending on the calculator that you are using, sine, then the value that you've been given. We get 17.5 degrees is correct to one decimal place. Now we are interested in the values of theta in the quadrants where sine theta is positive. Sine theta is positive in the first quadrant and the second quadrant. Now that makes our reference angle part of the solution because this is in the first quadrant, and in the first quadrant sine is positive. Now we are going to look for the other, or we can write this using the general solution. The general solution for this, we are going to say theta is positive. Okay, theta equals to 17.5, which is our reference angle, plus k times the revolution or the period of the sine function. Remember, the sine function has a period of 360 degrees, where k is the element of integers. So k can be a number 0, 1, 2, 3, or minus 1, minus 2, minus 3. So this is our first general solution. But we are interested in quadrants where sine is positive, and sine is also positive in the second quadrant. So in the second quadrant, we will have theta equals to 180 degrees minus the reference angle plus k times 360 degrees. Remember, 360 degrees is the period of the sine function. K is any number, any whole number, 0, 1, 2, 3, minus 1, minus 2, minus 3. The second general solution is theta equals to 162.5 degrees plus k times 360 degrees. So these are the two general solutions to sine theta equals to 0.3. Let's now look at another problem. Here we are required to determine the general solution. We are given 5 tan beta plus 15 degrees equals to 5 over the square root of 3. If you look at the left hand side, we have 5 tan of something. We cannot work with 5 tan something, so we have to divide by 5 on both sides, so that on the left hand side we are only left with one trigonometric ratio with no coefficients. Now we can find the reference angle here by using the arctan of this. So this is our reference angle. Now we treat this b plus 15 degrees as one angle. You treat it like we did with x, like we did with theta. So you treat this as one angle, and then you find your reference angle there, plus k times 180 degrees, where k is the element of integers. Remember, the period of the tangent function is 180 degrees. This part here includes the period of the function that you are working with. The period of the sine function and the cosine function is 360 degrees, and the period of the tan function is 180. Then from here we can simplify. The arctan of 1 over the square root of 3 is 30 degrees. This is our reference angle. We can further simplify for beta. So our beta will be 15 degrees plus k times 180 degrees, where k is the element of integers. This is one of the solutions, which will be in the first quadrant. Our reference angle is 30 degrees there. Or we can also find this in the third quadrant where tan is positive. Remember, we are interested in the values of beta where tan is positive, because this equation is positive. Tan is positive in the first quadrant, and it is also positive in the third quadrant in 180 degrees plus the reference angle. We can simplify this to get beta as 195 degrees plus k times 180 degrees, where k is the element of integers. We come to a problem where we have a sine of some angle equals to the cos of some angle 2x. But we remember that sine and cosine are co-functions of each other, which means we can express either cosine or sine in terms of cos if we write it in this manner. Remember, the cos of 2x is the same as the sine of 90 degrees minus 2x. If we use our knowledge of the reduction formula, this is in the first quadrant where sine is positive and it changes to its co-function, so we can reduce it to cos 2x. But if sine x minus 30 degrees equals to sine 90 degrees minus 2x, that simply tells us that these angles must be equal. We can drop off the sine and only take the angles because they are equal. The only way that the sine of these can be equal to the sine of that is when the angles are equal. So we simply drop sine and sine, and then we are left with that. We can simplify this to get 3x equals to 120 degrees plus k times 360 degrees, where k is the element of integers. Now, when you solve for x, or you're trying to find the general solution where you have a problem that equates a sine and a cosine, and then you use this knowledge, you must look for the intervals where sine and cosine are positive. If you look at the equation, it says that positive sine equals to positive cos. So you must be interested in the quadrants where both are positive or both are negative. It could be, if this was minus sine and that minus, they will still be positive. So we are interested in the quadrants where both functions are positive or are negative. So we could take this solution as the first quadrant where the two functions are positive in the first quadrant, and then now we can go in the third quadrant. We know that sine and cosine are positive in the first quadrant and they are both negative in the third quadrant where only tan is positive. So we take it to the third quadrant, which is 180 degrees plus our reference angle. We can simplify this to give us x equals to 100 degrees plus k, where k is the element of, it's 100 degrees plus k times 120 degrees, where k is the element of integers. So we can actually write the final solution as x equals to this, or x equals to that. Let's look at problem 2. If you look at this problem, it's similar to what we have dealt with in the previous problem, where you have to use your knowledge of co-functions to find the solution to this. But also, if you look at the angles here, they're the same. It's the sine of x plus 15 degrees to the cos of x plus 15 degrees. We know that if we divide both sides by the cos of x plus 15 degrees, we can end up with a function that we know. We know that the sine over cos is the tangent function. So this can be written as the tan of x plus 15 degrees, simply because the angles are equal here. That's why we used this approach. We didn't use the same approach in the previous problem because the angles were not the same. Here we have x plus 15 degrees, x plus 15 degrees. That's why we are able to divide both sides by the cosine and then change this to the tangent function. We can now find the general solution to this. On the left hand side, we only have the tangent function and some numerical value on the right. So we can use second function or shift the tangent, then 2 to find our reference angle. Like in the previous problem, treat x plus 15 degrees as any angle that you would, like theta or just x. So we leave it as it is. We find our reference angle here. We remember that the period of tan is 180 degrees. We multiply it by some k, where k is the element of integers, and then you simplify to arrive at x equals to 48.4 degrees plus k times 180 degrees. Look, we are interested in the intervals where tan is positive, and this in the first interval, the first quadrant. So we can also find another solution where tan is positive. We know that tan is positive also in the third quadrant. So we could have 180 degrees plus our reference angle in the third quadrant, and then simplify to arrive at that. Lastly, let us look at the quadratic trigonometric equations. Let's say you've been given some quadratic equation or trig equation like this, and you were required to solve for x, the element of 180 degrees and minus 180 degrees and 180 degrees. We cannot simply equate anything. There's nothing to equate here because we have some complicated functions on the left hand side and 0 on the right. But we can factorize this. We can simplify this like we would any quadratic equation with the variable x. So if you look at this as x, this would be the same as 2x squared minus x minus 1. So we can use our knowledge of factorization to find the factors of this. So we simply factorize that, and we will have cos x is minus 1 over 2, which is the same as 0.5, or cos x equals to 1. Now we can start with this one. If you look at this, this is now the simpler form that we're looking for. On the left hand side, you only have cos x and some numeric value on the right. So we can use this to find the reference angle. Remember, when you find the reference angle, you use the positive value instead of the negative value. Second function, or shift, cos, then you press 0.5. That will give you 60 degrees. 60 degrees is in the first quadrant. But if you look at this equation, it says we must find the values of x where cos x is negative. Cos x is negative in the second and the third quadrants. So the first solution, we go in the second quadrant in 180 degrees minus the reference angle. So we are going to have 120 degrees plus k times 360 degrees. Remember, k is the element of integers. You always put this because we are starting with the general solution first. Then we will be able to find the values that fall in that interval. So we'll start with the general solution here. Now this is the interval in which cos x is negative, 180 degrees minus the reference angle. But it is also negative in the third quadrant in 180 degrees plus the reference angle, which gives us 240 degrees plus k, where k is the element of, k is the element of whole number. So it's k times 360 degrees, and k is the element of integers. We have solved for this part of the solution, but we still have cos x equals to 1, which is also in the simplest form. So to solve for this, we find its reference angle. Second function, or shift, cos, you press 1, you get the angle 0. This is the general solution that we have, it's just 0. And we know that the period of cos is 360 degrees. Now, these are the general solutions to the problem that we've been given, but we were not required to find the general solution. We are required to solve for x where x falls within these values. So if x is bigger than these values, it won't be part of the solution. So the best thing that we can do is to now use the k values to find the actual values of x that they want here. We said k is the element of integers, not real numbers, the element of integers or whole numbers. So you can actually substitute k with any value between, let's say, 0, 1, 2, or -1, -2. Let's start with k equals to -1. And we substitute k equals to -1 in this general solution, and that general solution, and that general solution, and see what we get. When we substitute it in this, our answer is minus 240 degrees. Minus 240, it's minus 240 degrees is outside this interval, so it cannot be part of the solution. We substitute k equals to -1 in this. When we substitute k equals to -1, we get minus 120, which falls within this interval, so it will be our solution. Then we substitute again -1 in this. When we substitute -1 in that, we get minus 360 degrees, which is outside of the interval. Now let's try k equals to 0. If we substitute k equals to 0 in this, we will get 120. When we substitute k equals to 0 in this, we get 240. K equals to 0 there, we get 0. Let's try k equals to 1. If we substitute k equals to 1 here, we get 480. K equals to 1 here, we get 600. K equals to 1 here, we get 360 degrees. We could substitute k equals to -2, -3, but we realize that as k becomes smaller and smaller, the values becomes too negative and bigger. They don't fall within the interval, so it would be just a waste of time. Also, we could go on and substitute k equals to 2, 3, 4, 5, but the values keeps on becoming bigger and bigger, so they don't fall within the interval that we are interested in. So that's why I only used k equals to -1, 0, and 1. So at the end, you see that the solutions that fall within this interval, it's minus 120 degrees, is 0, and 120 degrees. Therefore, we can write the final solution of x. X is therefore minus 120 degrees, or 0, or 120 degrees.